to the CPPC seminar. So our speaker today is Yong. Yong is visiting UNSW for 3 weeks, and he's an expert on parity violation, on precision calculations, and effective field theory techniques. And today he will be telling us about parity violation, a window into standard model precision and quantum foundations. And I should say he's recently started a faculty position at the Institute of Modern Physics after having done postdocs at the ITP and TD Lee Institute in Shanghai. Over to you.
Thank you, Michael, for the introduction. Actually, I'm very happy to be here to talk about our recent work on parity violation. So this talk is based on the 3 papers shown at the bottom. One was finished when I almost completed my PhD degree, and the other 2 were finished last summer or last winter, depending on where you go. So let me start with the outline of my talk. I will first briefly introduce why I care about this topic. And then I will go to the first part of my talk, which will be on parity violating electron scattering. Especially, I will focus on the Moller experiment and the J-Lab. And I will talk about the experimental setup and the precision target of this experiment, and then on the theoretical prediction aspect. And in the second part of my talk, I will talk about our recent work on quantum entanglement, focusing on the effect of parity violation and also the environmental effects. And I should say that the parity violation was barely investigated in the past, and the environmental effect, people never talk about that. I will point out that the environmental effect will be very important for a correct understanding of quantum entanglement in certain cases, of course, and then I will conclude. So let me start with the very beginning of the introduction of neutrinos, where Pauli actually introduced the existence of neutrino to explain the non-discrete or continuous spectrum of the electron from beta decay. And then soon after this proposal from Pauli, Fermi had his theory for beta decay in 1933. And then the question is, we have a neutrino, we have this theory, and how do we detect the existence of neutrinos? Actually, the first suggestion was given by a Chinese physicist called Gan Chang. He proposed during actually World War II, and suggested that we can indicate the existence of neutrinos by measuring the recoil energy of some atoms. Somehow this experiment was not done, and the first observation of neutrinos is actually coming from another so-called Cohen rings experiment from inverse beta decay, as you can see from equation 1 here. And now we have detected the neutrinos. We have this Fermi theory. We can consider, for example, the cross channel, where you have incident high energy, for example, electrons or neutrinos. And then from dimensional analysis, you will see that the cross section will diverge if you go to a very high energy, where GF is a Fermi constant. So in the following, we will know the story, so I will be very brief about the development of the standard model of particle physics. The first thing I want to mention is parity violation from Li and Yong, and then the Wood's experiment verified the parity violation in weak interactions, and the parity violation means chirality, which helped the development of standard model of particle physics, especially at the very beginning. It helped unify the EM and the weak interactions by Glashow, Wimberg, and Salam. And this unified theory was not proved to be renormalizable until 1971 by Truft and Veltman. And then this theory becomes predictable and also testable. So the example we can look at is, for example, this simple process, muon-neutrino scattering of electrons. And in the high energy limit, the cross section will only depend on one unknown parameter, that is the weak missing angle. You know the central mass energy, you know the Fermi constant, so you can, by doing experiments, you can have a value for this weak missing angle. Experiments include muon-neutrino scattering of electrons, which is very clean because it's purely electronic. You can also have neutrino scattering of protons or nucleus, and then you have some slightly dirty environment from the hadronic physics. You will see from the very early measurement that the experiment value, as shown here, is very close to the current number of the weak angle, close to 1/4. And later, that measurement is only at one point. You only measure the total cross section. Now, if you measure the angular distribution as a function of the scattering angle, for example, as shown in this plot, you will see that the predicted differential cross section is a function of this scattering angle, and it will depend on the weak missing angle I just mentioned. You will see that different models, like the hybrid one or the weak interaction, the Wong-Gasala model, you will see that their predictions are different. So this is actually the early experiment that excluded this so-called hybrid model. So the difference between the two is that in the hybrid model, the red Hamilton, what we call the red Hamilton, is also a doublet. That is the difference. So it seems that we can use parity variety electron scattering or neutrino scattering to test theories. And nowadays, the parity variety asymmetry, which I defined here, you have either a left-handed polarized electron or beam and a right-handed polarized beam. You find the difference in the cross section, and then you normalize by the total cross section, which will give you the so-called parity asymmetry. And shown this plot, on the y-axis, you have the absolute uncertainty on this asymmetry, and on the x-axis, you have the total asymmetry. The first experiment was done by SLAG E122 experiment, and you'll see that the relative uncertainty is like 10%, as you can see from this dashed line here. There are many following experiments on this, as you can see from these dots. The main point is that we are now approaching the precision that is so high that we can use these high precision experiments for some model precision tests. And for among all those future experiments I want to mention, for example, there's two experiments. One is the Moller experiment at the JLab, corresponding to electron scattering, which I will discuss in following slides. And you will see that its precision is very high. We'll approach the percent level precision. MESA T2 is another experiment by Germany. Probably Michael knows more about this experiment. It is polarized electrons scattering out protons. And then you also measure the so-called proton weak charge. And then you can extract the weak missing angle. So these two are the leading experiments in the near future. In the past, I only focused on the theoretical prediction for the Moller experiment. So let me tell you more about this experiment. As I mentioned earlier, this experiment will be performed at the JLab. You prepare high energy electrons, longitudinally polarized. The energy of the incoming electron is like 11 GeV, and you then use this high energy electron to hit some target. In their case, it will be the liquid hydrogen target. And the electron will scattering of the orbital electrons, and then you will have some scattered electrons. That will be your signal, which will be separated from the background in this hybrid toroid system. And the resulting event will be your signal, which will be analyzed here. In short, the experimental precision target will be 0.2 parts per billion for this asymmetry. So it is a very high precision experiment. So for the experimental setup, they have some cut on the polar angle, which they require that. So this is what I call the scattered electron, which they call Moller electrons. They require the scattered electron to be like within this tiny period. But there's no cut on the azimuthal angle, so that you will see actually a ring for the distribution of the electrons. Now with this high precision experiment, what would be the interesting physics we can look at? One example is its impact on the fermion operators. You can imagine you have some heavy physics that has been integrated out, which then induce some four-lepton operators. And this effect has been previously studied in this paper by Bukowski and his collaborators, and it is found that you can constrain your physics at above the TeV scale. You can also have some specific UV models like the left-right symmetric models, where you can have the doubly charged Higgs, such that your electrons can firstly annihilate into this doubly charged Higgs and then decay into the electron pair. This has been studied in 2018 by Bupao, and the other possibility was investigated recently by this author Thomas Van Williams. They considered the dark photon, and they found that Moller experiment can put a very stringent limit on these kind of models. So the range is indeed very, the potential is indeed very rich. And in talking about the for electron operators, I shall point out that we have the Back scattering, for example, done at the lab. Now, if we want to perform a global analysis on the EFT operator, we will see that Baba is not enough to constrain all the 4 lepton operators. That's not just one; there are 3. So you cannot constrain all the 4 electron operators from Baba again. So you have to include the low energy experiments, and that one is just the current most precise one, which was SLAC E158. By including this experiment and the Baba experiment, you can simultaneously constrain the 3 lepton operators. So it is indeed indispensable for a global analysis on the EFT operators. I should also mention that this operator, if you look closely, this is the 4 left-handed leptons with the first generation leptons. This operator will also modify the neutrino decoupling of the universe by introducing new interactions. And Yong in the audience is an expert on neutrino decoupling. I myself also had some papers on EFT operators, modifying neutrino decoupling of the universe in both the low energy EFT case and also the SMAP case. I will not talk more about this today because that is another topic. How about the theoretical progress? The first calculation was done in the 1980s. It was they calculated the leading order contribution to the Moller scattering, electron scattering, and the Derm and the Marciano then found that this analytical expression for this asymmetry is in back here. The Y can be understood as the scattering angle Q squared, just momentum transfer. And you'll see that at tree level, this asymmetry is proportional to this combination. And we know that in the Sun model, this is very close to 0. So that means the Sun model predicts that this asymmetry is very tiny, which means it will be very sensitive to new physics, because in new physics, you may not have this kind of suppression. How about the next leading order contribution? This was first done by Charnetti and Marciano in 1996. And they found that you can always do a computation like this. You can always do the asymptotic expand based on the Wick, the fermion constant, and then the couplings, which would be the gauge couplings. So you can find the first loop, the one loop contribution to this electron Wick charge, and by fully compute the one loop contribution to this electron scattering, Charnetti and Marciano found that the tree level asymmetry is further reduced by about 40%, which means this APV is even more sensitive to new physics. Now, for the Moller experiment I just mentioned, there is a series of work by Alexei Jacobs and his team members. These 2 calculations to involve, so they only partially estimated the contribution to APV, and they found that if you want to match the Moller precision, which is 0.2 parts per billion, you have to finish the full 2 calculation. This hadn't been done until we started to tackle this problem. This calculation is very challenging because the number of Feynman diagrams at 2 loops is already very large, and if you do it by hand, it is almost impossible. And it is also very easy to find silly mistakes. So our goal is to use computer algebras to finish these 2 loop calculations. And I will quickly go through the techniques because this is not a technical talk. So I will just have 3 slides to talk about the techniques we used to finish these 2 loop calculations. The first one is whenever you write down the amplitudes, you have to reduce the tensor integrals into the scalar ones. And this can be done by known methods like known as the fermion reduction. So you can reduce the tensor integrals as given here by the scalar ones as given here. For the scalar one, here you have a large weight in the denominator. How to solve that? This is called the integration by parts. You can apply this technique to find a recursive relation. As you can see from this example here, the weight is reduced by 1. Now, by repeatedly applying this recursive relation, you can reduce this high weight integral into a basic one, which we call the master integral, which is usually very simple to finish analytically. And in the case where we have non-perturbative corrections like the photon self-energy corrections, because this is a low energy experiment, you have to deal with the non-perturbative correction to the photon self-energy. So we did this by using the dispersion relations, which you can always relate the full amplitude with its imaginary part by using the Cauchy theorem. Okay, so this is the non-perturbative part. The final challenge comes from integral with multiple scales. We will have multiple scales in your loop integrand. It is known that it is very challenging to obtain the results analytical. So I shall stress that I want to focus on analytical results because we want to ensure that there's no uncertainties coming from large number of cancellation, which will introduce some uncertainties that is not physical. So that's why we are focusing on obtaining analytical results. For these multiple scale integrals, you can do some simplification. For example, if I assume all the fermion lines, which are basically electrons, are massless, then you can finish this integral. And we do the UV, we absorb the UV, we regularize the UV divergence by Dimrag, and we regularize the IR divergence also by Dimrag. In that case, you will see that you cannot distinguish UV divergence from IR divergence. But that is not a problem, which I will give you also a solution later. Remember, we are looking at corrections proportional to the Fermi constant. So that means this full expression may not be that useful because it contains corrections that is of higher order. So that means what we really shall do is to expand this full expression by assuming MZ is very large and then do asymptotic expansion. You will see that the result is very simple. Do we learn any lesson from that? Actually, that is exactly the idea of expansion by regions. So, for example, for this diagram, we just have 2 scales: the momentum state variables and then the MZ, the Z max. We just put these 2 scales on the axis, and then you do asymptotic expansion in each region. In between, you always get scaleless integrals. So that is assumption vanishing. So you only need to consider these 2 regions. And in the first region, by the asymptotic expansion, you will see that immediately you can finish this integral like in few minutes. The result is exactly the same as the previous one, which I took like 1 week to finish. I tackled this problem when I was a student. And if you look at the corresponding diagram corresponding to this asymptotic expanded integrand, it actually corresponds to this diagram, where the Z probability has been shrunk to 1 point, and you will. And so that's why it gets much simpler. Now, in the other region, where the low momentum is comparable to the heavy mass scale, you again do a similar asymptotic expansion, and you arrive at this result, which is of higher order and can be neglected. So in summary, you only have 1 conclusion from this region, which is much more easier to evaluate than the full expression. And if you also have some experience with the matching between UV theories, specific UV theories, and the EFT operators, you will see that this method of regions is exactly the idea of functional matching developed recently by Gohan and collaborators, these people. So that is basically the techniques we applied to finish this project. And I only show here the topologies relevant for 2-loop Moller scattering. The number of diagrams is very huge. So So it is easy to find to have some mistakes, like probably you already heard the story about Kinoshita. He calculated the lepton enormous magnetic moment, and in the past, his result tells us that there's a significant deviation about 3 sigma between theory and experiment. Later, there's another group which has done the calculation independently, and they found that the deviation from the solar model is very tiny, like about 1.5 sigma. So what is the reason? And they checked their calculation carefully and found there's some error in their conventions for the Levi-Civita tensor. So this lesson tells us that for loop calculation for precision projects, it is essential to have independent calculations in order to ensure that your result is correct. So for us, we have 4 people, so we make sure that each diagram is cross-checked at least by 2 of us. So in that way, we make sure that our calculation is correct. So I just present our final numerical results for all the 2 contributions. The first line corresponds to the tree level result. The middle 2 lines correspond to the 1 loop result. As I commented earlier, you have about 40% reduction from including the 1 loop corrections. At 2 loop, you see a similar conclusion. So the subscripts here means the first number means the total number of loops, and the second number means the total number of closed fermion loops. And you see that the fermion loop, you see that the total correction from if you have 2 closed fermion loops, you have a negative correction. If you have just 1 closed fermion loop, you have positive correction. That means similar to the 1 loop correction, you have an accidental cancellation between these 2 cases. And if you sum up these 2 contributions, we arrive at a 2 loop prediction for the Moller scattering, which is about at the fermion level for the electron weak charge. And for the Moller experiment, the planet precision target is about 1.1, slightly bigger than the theoretical uncertainty. So that means the theoretical uncertainty is under real control. Now the question is, how about the bosonic loops? Those 2 correspond to the diagram with closed fermion loops. So for the diagram without any closed fermion loops, we just estimate its order of magnitude based on the hierarchy of tree level and 1 loop results, which is also a standard estimation in literature. And we found that the pure bosonic loop contribution is 1 order of magnitude smaller than the experimental precision target, so still under real control. So with that, with the theoretical uncertainty under control, we will be sure that in the future when data is collected at Moller, we can have a correct interpretation of the final results. And that is why the Moller experiment has been finally approved after like 10 years. So to quickly summarize, we have seen that the Moller experiment, which is actually an investigation on parity violation, has a rich physical potential, including precision tests of the standard model and also like neutrino decoupling in the universe, I just commented. It also helps lift flat directions in the snapped global plate. It also helps constrain the particular space of spatial UV models. Now, since this year is the International Year of Quantum Science and Technology, I think it is a good time for me to also introduce the second part of my talk, which would be on quantum entanglement. But before that, are there any questions on my first part?
So you know that higher loops are subdominant.
Yeah.
Will become subdominant.
Yes. Other questions?
So maybe I'll ask another one. So how accurate are your dispersion calculations? The non-perturbative ones?
Oh, that is a good question. Actually, for us, when we input the numerical values, basically that introduces uncertainty in the fermion masses.
Yeah.
And you can see from this uncertainty here is actually coming from parametric uncertainties, you see that this is very, very small. So,
I was just wondering if you have like by light contributions or something. Light by light contributions or something somewhere.
Light by light. For us, we are directly using the should I say the hadronic final state of electron scattering.
Oh, I see.
Yeah. From that data, we extract the
Yeah.
input of the parameters. Okay, thank you for the questions. Maybe this part is too technical, but let me go to the second part, which is much less technical. So it is on quantum entanglement. So the targets of our studies will be qubits. And for qubits, we consider, I will just introduce two cases. The first one is low energy qubits, for example, entangled photons. And there are known ways to generate entangled photons, for example, from the cascade decay of calcium. You can also obtain entangled photon from, for example, electron positron annihilation. And this is actually the first process investigated by CSU, the known Wu. She and her collaborator measured the angular correlation between the two entangled photons. But at that time, they didn't see any entanglement. And nowadays, I believe everyone knows that the entanglement study using photons has been well established. We already see that the Nobel Prize was given by those significant figures in 2022. So how about high energy qubits? So for high energy qubits, the first example was one example is the TD bar at LGC, where you can produce a pair of top quarks as shown in this plot. And this TD bar is entangled because of angular conservation. And now, just like last year, the Atlas collaboration claimed that they have observed quantum entanglement between these two top quarks, and their results are shown on this plot, where the y-axis is just a measure of quantum entanglement, and on the x-axis is just the invariant mass of the top pair. And the requirement that as long as this measure is below -1/3, you can claim entanglement between the top pairs. They only see the entanglement in this invariant mass spin, but the significance is very high, about 5 sigma. So their results have been published in Nature, and this claim is obviously correct. Now, if we want to study quantum entanglement at colliders, as you will see soon, luminosity will be the key ingredient, at least one of the key ingredients. So I will justify this soon. For luminosity, it seems not to be a big problem because, for example, for BS3, which has produced like 10 billion J-psi particles, number of particles is already very high. In the future, there are proposed colliders like the lepton colliders like CPPC, FCCE, IOC, inner ones, and click. Those are the leptonic colliders. We also have the proposed tau-charm factories. Maybe this is too small, but the point is the luminosity is very high. The number of J-psi particles that can be produced in 1 year is much more than the total number of J-psi particles accumulated at S3. So luminosity is not a problem, at least at this moment. So luminosity is good, and we know how to produce entangled pairs. And then the next question is, how do we build up a formalism for the study? This is usually called quantum tomography in literature. I will just use formalism and abstraction in the following discussion. And since we focus on spin half system, we can always expand the system in the SU2 cross SU2 Hilbert space to write down the general density matrix for this system. And you will see that you only have 3 parameters from this polarization vector, 3 from this one, and 9 from this one. So you have a limited number of unknown parameters. So how do we determine those unknown parameters? For the polarization vectors, it's simple. We can always look at the decay in the rest frame of the decaying particle. And then from the fitting of the angular distribution, we can extract the information of the polarization vectors. Now, how about the spin correlation matrix? We have non-unknown parameters. And if you want to determine these non-unknown parameters, you have to look at the joint angular distribution of the two final fermions. And from this joint angular distribution, you will be able to determine the spin correlation matrix among that two fermions. So that is, so we have the knowledge to reconstruct the density matrix. And once we have the density matrix, we can then study quantum entanglement based on the standard criterion, for example. Usually when people obtain like the density matrix, the underlying assumption that they always assume the fermion pair in the final state is entangled. But as you will see shortly, this is not guaranteed always. For example, if we want to investigate the entanglement between the fermion pairs, we can use the so-called concurrence as a measure of quantum entanglement. The concurrence is related to the density matrix through a spin flip of the second system. And then from this new matrix, which is related to the density matrix, you can calculate its eigenvalues. And then the concurrence is related to its eigenvalues. If its value is 0, that means there's no quantum entanglement. If it is non-zero or 1 means maximum entanglement. As long as it is apart from 0, you can claim you have observed some entanglement. For example, for the J side decaying into different hyperfinal states, you can start from the density matrix and calculate the concurrence. The plots are given here. The x-axis is just the scattering angle, and the y-axis is the concurrence. You see that as long as you're away from the far forward or far backward regions, you will see some entanglement between the two fermions. You can also perform a similar study for total. The result is even more promising. You can see that the maximum entanglement can be achieved when you are at the transverse plane of the final fermions, which is top. But again, if you are at the far forward or far backward region, you wouldn't see any entanglement. But I should point out that even though there's no entanglement, there's still a quantity called quantum discord, which you can use to study the quantumness of the system. That is beyond the topic of my talk today, so I wouldn't say anything about quantum discord. But if you're interested, we can discuss offline.
Is there a simple reason for that there is no entanglement in the forward and backwards region?
Usually, you can plug in the angles into the density matrix. You will see that it becomes separate.
Why is there a difference between different final states? Is it just the?
You mean in this case?
Yes. Is it just the?
There's the mass difference.
The mass difference, of course.
There's also the strong phase difference.
And
the EM form factor difference.
The form factor, I see. So how does the form factor go in there?
J side decay into J side is a vector particle.
Oh, I see. The form factor for J side decay into those
hadrons.
I see.
So that's why you have this different shape of curves.
And for tau, it's relatively simple because, well, I guess for tau, it should not matter if it's tau, apart from the mass, it should not matter whether it's tau or mu.
Exactly, but for muon, you have the problem that the muon is too long-lived.
The muon is too long-lived, yes.
That's why we pay tau.
So you cannot measure it. You cannot measure the decay.
Yes.
Okay, so this is on the entanglement, as I pointed earlier. The middle region will close to the transverse plane, you have maximum entanglement. So if you want to perform Bell tests, those are the regions we shall look into. For Bell tests, we have the original Bell equality, but that is practically very challenging because the two subsystems will share a common direction. And when you measure, for example, the spin along a certain direction, you have to simultaneously adjust this one common function between the two subsystems. These two subsystems, however, separated space-like, so it is not possible to do this. So an alternative is to use the CHSH inequality, where you calculate the eigenvalues of these spin correlation functions, and then you find the largest two eigenvalues. Now, if you sum up the two largest eigenvalues and compute its numerical values, if it is larger than 2, you can see that the Bell inequality is relative. And the maximum number is just 2 square root. It's just 2 square root 2. For this example I just mentioned, you can calculate the CHSE parameter from the spin density matrix or the spin correlation matrix. You will see that it behaves like this. For example, in this region, even though the entanglement is high, there's no violation of the Bell inequality. And this is a known result, that is Bell inequality is just a subset of quantum entanglement. I just want to make this point clear. Now, how about the parity variation on quantum entanglement? Okay, I need to speed up. So for parity variation, for the first example I mentioned, the photon case, it is a pure QED, so there's no parity variation. That's why people never talk about it. For the J-side decay, there's a large suppression from the QCD scale and the fermion Vega scale. So the parity variation is very tiny. So that's why people also wouldn't talk about this parity variation effect in these systems. But this is not generally true, as we have already discussed for the Z decay into lepton case. So the question we ask ourselves is, if we isolate the parity variation, what would be the impact on deltas? And the second question is, what would be our targets for this study? So I will answer each question in the following slides. The first case we studied is the spin 1 decay into 2 spin half particles. This is very simple. You can parameterize the Lagrangian generically as shown here. And then you will see that the system can be described by pure state as shown here. The parameters are related to the scalar and the pseudo-scalar couplings that I'm given here. And alpha here is just a parity variety parameter. You will see that in this simple case, the CHS parameter and the concurrence only depends on this parity variety parameter alpha. And especially if alpha is vanishing, you can see that the maximum entanglement and the maximum variety alpha can be achieved. How about the system we have already measured? We have measured the lambda, and also the C particles, and also the sigma hadron. And their alpha values are given shown here. You can see that perhaps the ideal targets would be using the C hadrons, because their alpha values are much more smaller in magnitude. In the second case, we consider spin 1 decay into again a pair of fermions. We consider two generic couplings, the vector coupling and the axial vector coupling, where the axial vector coupling will be a measure of parity variation. And we show the results for the CHSA parameter and the concurrence in these two plots, where the y-axis, as I mentioned earlier, is just a measure of parity variation, and the x-axis can be understood as the mass of the final state fermions. And you see that there's basically a 1-to-1 correspondence between these two diagrams. And now, if you want to increase, for example, the entanglement or the variation of inequality, one possibility is to go from heavy fermion to light fermions, like tau to mu states. The other possibility is to increase the parity variety coupling. And the examples include you go from d quark to down quark to leptons. So you have two directions to increase the entanglement within the two subsystems. Note that these two plots are obtained at the transverse production plane. If you move the detector away from the control production plane, you will see a similar behavior. So that means if at the transverse production plane where the background is probably less severe, you can accumulate more events by moving the detector away from the transverse production plane. Shown in these two plots. So now what is missing? I'm finally coming to the environmental effect. So when people study quantum entanglement, you can look in the literature, they never talk about the particles interacting with the environment. But we know that the environment, for example, like colliders, is not a vacuum. So that means the spin and the momentum can interact with the environment. That will cause the decoupling, so-called decoupling effect or depolarization. this effect may become significant, as I will show shortly. And if you didn't include this interaction with the environment, you may have some incorrect result, which I will quantify shortly. To make that point, let's look at the detectors in a more detailed way. So inside the detector, we have the beam pipe as shown by this red line. Inside the beam pipe, it is basically vacuum state, so the interaction is significantly reduced. But outside the beam pipe, there would be the so-called main chamber. In the main chamber, there would be gases, the gas, and the particles could interact with the spin. For example, the spin could interact with the orbital angular momentum of the gas, and it can also interact with the spin of the gas. So that would cause a significant change, maybe a significant change in your density matrix. So in order to avoid such a complicated case, we consider the simplest scenario, where we require the particles decay inside the beam pipe.
So how large is what is the size of the beam pipe? The volume where it's when you collide objects. So
the value of this wouldn't matter for us because we want to consider the particle decay inside this beam pipe. Otherwise, if the particle travels outside the main chamber, for example, it interacts with the material, that would be too complicated. We don't know how to quantify that effect. So we consider the simplest case. The particle only decay inside the beam pipe. So that would have some limit on the left hand of the decaying particle. So based on this requirement and the radius of the beam pipe, we have selected those particles for the study. For example, for Z decay into tau or Chang area, or J side decay into Crissy hyper state. We have checked that these particles would have a large possibility decay into the beam pipe, such that they only interact with the environment inside the beam pipe, which is just a magnetic field. For the magnetic field, we know how they interact with the momentum. We just rotate the momentum based on the Lorentz force. And for the spins, it is much more complicated because we have a time-dependent equation. And to solve this equation, we realized that the exponential factor shows that this is usually solved by the so-called magnetic expansion. And the magnetic expansion will have an exponential factor. For us, the exponential factor is very small. So that means we can truncate at the first order magnetic expansion to arrive at the rotation on the spins. So now we know how to rotate the momentum. We know how to rotate the spins. We know how to replace the density matrix. And this is the point I want to stress. In literature, as I mentioned earlier, they consider the density matrix as the one at the production point. There's no such real error. I just want to make it clear that there's a particle produced and then decay. But in literature, they just consider the decay is happening at the production point. So they then use this density matrix to study quantum entanglement. But obviously, this is not the correct case because you have, even inside the beam pipe, you have the magnetic field, which is along the beam direction. So now let's consider the real case. You have one charge fermion. Charge fermion produced here, Kelvin above. It will then be banded by the magnetic force, and then it will travel for some time, and then it will decay because it is unstable. So suppose it is traveling for a time of t1. The other particle can travel at a short time, or another time, and then decay at another point. So then you measure the decay products, and then using the decay products, you infer the spin information of the decaying particles. So that really means you shall use the density matrix at the decaying point instead of the production point.
So how does this impact the TT bar entanglement at LHC?
That is a good question. TT bar, the lifetime of TT bar is too short. So, yeah, so this.
I see. So it remains entangled at least on the time scale when the.
Yes. Lifetime is too short. So the impact from the environment is marginal. So now, if we have considered this environmental effect, now we shall really replace the spin and the momentum at the spin and the momentum at the decay point. And then we use that density matrix to study quantum entanglement. Now, clearly, the density matrix is not time dependent. How do we deal with this time dependence? We don't have any access to the data. BES3 is not does not provide any open access to the data. So our assumption is we just assume that at each phase space point, luminosity is high enough so we can average over the time dependence. To do that, we just investigate two scenarios. One is Gaussian probability distribution function. The other one is the Blossom case. And we found that the conclusion is the same. For the uncertainty, we just use the time of flight system uncertainty time resolution, which is given here for BES3 and the lab. And then we investigate the impact on quantum entanglement. The conclusion is, the question we can ask is how large is this environmental effect? If it is too tiny, like TT bar, no one cares. But if in some cases that are important for your study, then you should really care about it. So to answer this question at the top, we know that the spin precession and the momentum rotation are just unitary operation. So it wouldn't affect the eigenvalues of this matrix. So what we do is we just focus on the spin correlation matrix, CIJ. And remember, CIJ can be measured from the joint angular distribution of the finite fermions. And one key observation is that in the P or CP conserving case, you will have, for example, C2 equal to C21. Now I can define a quantity that is the difference between the two quantities. And then let me use the time-dependent density matrix to evaluate this difference. If it is non-zero, that means you have some environmental effects observed. That is indeed the case for the candidates we have just selected. C for J psi decay and tau and lambda C for Z decay. In the C case, we found that we will just call this the spurability and the CP variation effect. It is of order 10 to the negative 3. This is very large. Still, I shall point out that this cannot be measured currently at S3. It could be measured, for example, as a next generation tau-chum factory like STCF, I mentioned at the very beginning. So at that stage, if you don't include this environmental effect, your conclusion about the P or CP variation may be misleading or even incorrect. Okay, so in the last 3 minutes, let me talk about new physics. So new physics, people have been investigated, for example, EFT modifications to the spin density matrix. So whenever you introduce new interactions, the density matrix will be modified. So that is expected. And you can also use the quantum entanglement as shown in this plots by these authors. They showed that you can use the distribution of the entanglement to distinguish different kinds of interactions. For example, this is the vector type for fermion interactions. This is tensor type for fermion interactions. And also in my previous discussion, I always introduce the Lagrangian, which means I rely on my knowledge of some quantum theory to do the calculation. The question is, do we have to introduce any quantum theory in order to do the study? The short answer is no. And the reason is as follows. For example, let's consider a spin 0 decay into 2 spin half particles. We only have one freedom, that is the momentum of the daughter particles. So that means you have these relations. You have a few parameters unknown, like the E1K, B2K, C0, C2, and C5. Now, if we assume there's no special direction in nature, which is the axiom we will take, you can use angular momentum conservation to further reduce the number of unknown parameters. For example, you will have this relation for these two polarization vectors. You will also have this relation between C0 and C5. And now you can relate the CHSE parameter with the polarization vector like this, and the concurrence with the CHSE parameter together with the Epsilon parameter we define at the bottom, which is nothing but a deviation from any QFT. So in QFT, the Epsilon is strictly 0. If you observe a non-zero Epsilon, that means you may have seen some evidence or some signal of new paradigms beyond QFT. If you look at the experimental papers, they always assume that the issue is zero, except some experiments at a very early stage, which I've discussed in this slide. So shown in this plot is the concurrence as a function of the situated parameter. The solid magenta curve corresponds to the case where the deviation from QFT is zero. You have this solid curve. The shaded region, hazard region, correspond to negative probabilities, so it is precluded. The very first experiment that have done this measurement is from the Brookhaven National Lab. They measure the three parameters independently, and from their result, you can calculate that the deviation from the QFT is consistent with zero. There's an issue that the sign is incorrect. It corresponds to negative possibility. The uncertainty is too large, so still no conclusive conclusion. There's another.
I'm trying to understand what this means. So what does paradigm beyond QFT mean? So in QFT, I have to introduce local hidden variables. Is that?
Not that. For QFTs, this is a good question. So for QFTs, we always assume the Lagrange's permission.
Yes.
And the evolution of the system follows a unitary.
Oh, so you'll break unitary evolution. Is that what you're?
One possibility. There's also the CPT variance. Maybe we can also relax that assumption.
Okay.
Yeah.
Fair enough.
We don't know. So I don't know the quantitative.
But unitary
but that is just
evolution
the possibilities.
But unitary evolution is not just QFT; it's also quantum mechanics.
Yeah.
I see. So you're also saying that in that case, I have to think of something beyond quantum mechanics.
Yes.
And also energy positivity, because CPT is then related to energy positivity. So if you saw something, so this
possibility happen to be go parallel. You can just be my case. So this is the first measurement we have found in literature. The second one slightly relaxed that assumption in this paper. For reference, we also included in this plot. The sign is not correct. The area is still too large. So after our paper was posted on arXiv, we discussed with the LHCb collaboration, and Yong is a professor at Peking University, and they redid their analysis without including any new data for their analysis in this paper. And they found that the process presented in this paper corresponds to a usual value that is slightly larger, but the uncertainty is reduced, as you can also see from this green plot. At the very beginning, I mentioned BS3, which has a very large number of statistics, but as I commented earlier, they all assume usually zero in the analysis, so there's no data from the BS3 collaboration. We have communicated with them. They are not redoing the analysis. Probably in the near future, we will see the plot for BS3. Okay, here's the summary. Maybe I can just skip the summary because I have too many to a lot on that. And let me thank you all for your time and attention, and also Michael for the invitation to make the SW, and also the Golden Goldfish request for this for the financial support of this trial.
Thank you very much. We already had quite a few questions, but time for more.
Yeah,
Yes, Yong?
I wanted to ask, so physically, why should the entanglement be related to parity? Is it because you couple two different spins and then you can kind of say that they are related, or why?
I didn't hear the first sentence.
Yeah, like physically, like why should it be related, like entanglement with parity violation?
Entanglement with parity violation.
Yeah, that's what you are showing, kind of.
Yeah.
So in physical terms, is it because you are like the theory couples differently to like right and left-handed? And then
I would put it this way: the interaction wouldn't matter. It is what mechanism that is causing the correlation between the two fermions. Parity value is just one way. You can also have parity conserving interactions. Still, you can observe entanglement like photons. So it is just the principle that gives you the correlation between the subsystems.
So you could have entanglement through other. It's not only due to parity violation.
Exactly. So R was just to tell you that the parity violation could, for example, disentangle or reduce or enhance the correlations between the two subsystems. And now let's say in the future, if you want to use weakly injected systems for information transportation, maybe you want to consider the effects from both parity violation and the environmental effect. People have been studying neutrinos. They want to use neutrinos to study quantum entanglement and quantum information, quantum computation. Neutrinos can interact weakly. Right?
So then you can
So
produce.
we want to consider the impact from parity violation.
Further questions? Can you go back to the environment effect once more? So has that been already shown, that environment effect, or included in any analysis? Or not yet, right? That's
Experimentally.
Experimentally, yeah.
That is a very good question. Experimentally, they only measure the density matrix at the production, reconstruct the density matrix at the decay point.
Mm-hmm.
So there's nothing wrong there. Theoretically, if you want to connect with theories,
okay, then you have
people
to evolve
always
it.
use
Then you have to evolve it.
Yeah, people always use density matrix at the production point,
Yes.
which is not always true.
Mm-hmm. So it's when you interpret the data, you have to pay attention.
Yeah.
Okay, no, that's a good point. Thanks.
You're saying on this that you take the time average of the density matrix at a point. I'm surprised that doesn't wash out too much information. Like, I don't know. Maybe I shouldn't be surprised. But what am I trying to say? So the density matrix at a point is just sort of tells you the makeup of the space at that point. And if you take an average of that over time in a beam like this, I would expect that would look the same, or at least have some sort of high amount of symmetry in the space. Make sense?
I cannot give you an answer right now.
Yeah, that's okay.
So if you think pictorially, it means if you wouldn't integrate over the time, it means you have a density matrix at each time slice of your history.
Yeah.
That is what we basically need about the ponies as I commented here. We don't have the access to the data. The data indeed has the time information. So you can really reconstruct the density matrix as a function of time. They can do that. As long as they wouldn't release the data, we cannot do anything here.
Okay, so you kind of just have to assume the time dependence for these different distributions. Right.
But BEST3 would in principle have the data to redo that and to include that.
Yes.
Okay. All right, that's fine. Yeah.
Any other question? Any last question? If not,
I have a question on Zoom.
yeah, please, Bruce. Sorry, I didn't see it.
No, that's fine. So thank you for the talk. For this environmental effect from the magnetic field as the particles propagate a small distance. I mean, you're analysing a very small effect. Are you aware of studies on other environmental effects and whether they might be of the same magnitude or smaller or larger? So, for example, passage of other electrons and positrons from the same bunch in the collision. So you see my question. I mean, there are other disturbances from electric and changing electromagnetic fields and particles passing, and which can be modeled somehow. Has that? I'm not aware of the status of that work. Have you checked what's been done?
That is a very good point. Thank you, Bruce, for the comment and question. So, due to our ability, we don't know how to simulate the environments with a bunch of particles, along with the particle we're interested in. So we don't know how to really simulate that effect, even within the beam pipe. If you are talking about the environment outside the beam pipe, that is even too complicated for us. We don't even know how to. We don't even have a clue to simulate that effect. Inside the beam pipe, it would be really desirable to simulate particles interacting with the surrounding other particles to have a quantitative result on the impact from the environment. But at this moment, I cannot say anything more about that. And
it just seems to me that if something is going to be claimed or studied, then one needs some sort of hierarchy of scales. That if we don't know exactly how to calculate these effects, fine, but such and such a rough calculation says that the effect should be smaller than this or larger than this. Without that, then it seems to me we don't have anything.
Well, I guess still for the top it would be fine, right? Because
no, for the top is fine because again you can perform such effectively. We are performing such a rough calculation because we look at the extremely short time involved that the top lasts, and it doesn't propagate a macroscopic distance, whereas these things do. So
if the lifetime is too short, I imagine that the environmental effect would be minimized.
Sure, but I think someone actually has to do a rough version of that calculation. I understand that a precise one is very difficult, but unless one has a rough estimate, I think one has nothing. And
yeah, I talked with my colleagues in China. We talked about this, but we haven't really done any calculation or simulation. We are thinking about that. Maybe at a later stage, I can give you some.
yeah, no, look, I sympathise, right? Because I was worrying about this at an earlier point for a measurement at Bell and Bell 2 that we were thinking of making, and I began to think about the problem and realised how hard it was. And I'm not aware of the work having been done elsewhere, but possibly because everyone has realised how difficult the question is. But at some point, someone needs to make an estimate.
Yeah, I agree.
Based on number of particles in bunch, how many bunches, what's their separation, how far apart in X and Y will the nearest unrelated electron or positron be? These sorts of things. Anyway, I think we understand.
Thank you.
Any other question? If not, then let's thank Yong for a very interesting talk.